Actually, I think Tristan's also traveled too, right?
I haven't seen him.
Yeah.
Japan.
So like literally most of our polar people are going this way, Lorenzo. I'm sorry.
No worries.
We are ready whenever.
We are recording it. It's fine.
Great.
Okay. I think we should just get started then. So it's my great pleasure to introduce Lorenzo Zampieri. He's a postdoctoral researcher at the National Center for Atmospheric Research. We've had quite the Boulder crew come through this semester, so it's nice to continue in that vein with our postdocs. So Lorenzo's research focuses on modeling approaches for Earth's climate, particularly targeting the polar regions and the sea ice system. You could probably guess that from the topic of his talk. He studied physics at the universities of Padova and in Bremen in Germany, and then he later pursued his doctoral work at the Alfred Wegener Institute, also in Bremen. He was a visiting scientist at the ECMWF for a period of time, and he is actually about to move back to Italy in June or July, one of those. June, okay, yeah, I was like trying to remember what you told me earlier, where he'll be working with the Euro-Mediterranean Center on Climate Change, so CMCC back in Italy. Sounds like a pretty sweet gig. And so at NCAR, he's mainly contributing to the M2 Lines project, which is this international collaboration to improve climate projections and use scientific and interpretable machine learning to capture unaccounted physical processes at the air-sea ice interface. So today, Lorenzo is going to talk to us about improving the subgrid parameterizations of modern sea ice models. So without further ado, take it away.
Yes. Let me start the timer. Thank you so much, Anna. I hope you can all hear me. Yes, I'm Lorenzo, and I'm a sea ice modeler. And yes, today I will talk about how we build models at the National Center for Atmospheric Research that then you also use and enjoy here at the university. So I will focus in particular on the heterogeneity of snow and sea ice and the impact that these have on the winter heat conduction. So to start, I want to show you this simulation, which is done with a very high resolution model. This is 1 kilometer in its ocean sea ice simulation. And you can see that the sea ice, it's a very heterogeneous medium. It breaks apart, it moves around. But today, the processes that we will focus on at smaller scale. So we are still in a subgrid regime at 1 kilometer. So very small scale processes, you can just pick one pixel in this image and then we will jump on that basically. So before I start with my science, I want to describe a bit the sea ice system and the way we modeled it. So this is a picture of sea ice taken during the MOSAiC expedition. It's summer, you can see there is light in the Arctic. This is the Atlantic sector of the Arctic in probably May, June 2020. And we can see the first thing about sea ice that I noticed personally is that it's a very flat medium. So it's much more extensive than its thick. It's up to a few meter thick. And this means that it's very susceptible to the forcings from the atmosphere and the ocean below. And the second thing we notice is that sea ice is bright. It's much brighter than the ocean in the gaps between these flows. It means that it reflects back to space a lot of the solar radiation, and it helps to keep the surface, atmosphere, and ocean in the Arctic relatively cool all year round. Another important thing to notice is that sea ice is heterogeneous in many, many ways. So you can see that the size of these flows varies a lot. Inside of each flow, we have heterogeneity in thickness. You will see that there are parts that are more flat, what we call level ice, and then there are also ridges where the ice is deformed. There is an heterogeneity when it comes to the brightness of the ice. There are parts which are snow-covered, which are very bright, but there are also melt ponds which absorb a bit more radiation. And then there is an heterogeneity when it comes to the composition of the sea ice. So it's not just ice, it's a much more complex system. We have snow that accumulates on top of it. We have fresh water, we have air bubbles in the ice. We have seawater, which is trapped into the structure of the sea ice. We have sediments that can end up being incorporated in the medium if the sea ice is formed close to the coast in shallow seas, and then there is biology, algae. And yeah, so it's a complex system. And now we can zoom back and we can see the kind of the situation in a pan-Arctic sense. Here you see the median ice extent observed historically, and this is the sea ice concentration at the end of the 20th September 2020. You can see that there is much less ice than there used to be. There is a lot of open water which can absorb heat in summer, and that's what we talk about when we say Arctic sea ice decline. We know that it's not a mystery that sea ice is affected by climate change. It's not as much the case for the Antarctic sea ice, where the situation is more stable, still with a lot of interannular variability. And of course the question is, okay, what comes next? And to investigate these questions, we need models. So I thought we could build together a very simple sea ice model. A basic feature of model that I would like to have is to be understandable, easy enough to implement, energy and mass conserving. This is very important for long integrations, efficient computationally because we want to run large ensembles and paleoclimate simulation, compatible with other modules, so it needs to be able to talk with the atmospheric model and the ocean model in a meaningful way, and also compatible with observations because we want to be able to verify our model predictions. And the way it goes is the following. So we start asking some question, how compact is the ice? And this defines the concentration variable, how thick it is, we define the thickness, what's the temperature, and we can define an enthalpy, how it moves around, and that defines the sea ice velocity. And basically we take these variables and we discretize them on a grid. In this case I'm showing an unstructured grid, but it might as well be a structured grid. It doesn't make a lot of difference. And basically we then solve some equations. First of all, we determine how sea ice moves in response to external forcing and also internal forcings. And this is basically a momentum equation where you can see that the acceleration of the ice is equal to the internal stresses, so how the ice is pushed around by the surrounding ice, the stress from the atmospheric wind, the stress from the ocean current, the stress of the bottom of the ocean in shallow seas where the ice can be grounded to the bottom. Coriolis term, and then there is a tilt term. It's basically if the ocean surface is inclined, the sea ice slides following the gradient of the ocean surface. Once we have the velocity, we can move around our tracers, and basically we solve the advection problem. These are continuity equations for each tracer. And after that, we determine how the sea ice grows, melts, and interacts with radiation, and this is what we call the subgrid parameterization and the sea ice thermodynamics. So let me describe a bit more in detail what's the panorama of subgrid parameterizations. We can have different levels of complexity. We can have a simple model that I'm describing here on the right-hand side, on the left-hand side, where we have a single sea ice layer with some snow on top. We have a linear temperature profile into the ice. And this is the simplest model description that probably we can have, which is currently used in a bunch of CMAP 6 models, so it's not outdated. And then we can have much more complex systems where we discretize the sea ice in multiple thickness classes. For each one of these thickness classes, we can have vertical layers. So in this case, we have a prognostic temperature and salinity profile. We can have prognostic melt bonds. We have a complex interaction between the sea ice and the radiation. We can have snow ice formation, biogeochemistry, and so on and so forth. So it can be fairly complex, I would say. And then, I guess you're familiar with this, but sea ice are typically not run alone. They are coupled to other model components, to the ocean and the atmosphere mainly. And this is what we typically call climate model. But we can also have third system models where these components interact with the biogeochemistry and also with human activities. These are very big beasts, and we typically integrate them to supercomputers. And this is a picture of the Chilean supercomputer that we use at the NCAR. Okay, now this was kind of an introduction to the sea ice world, and now we can jump a bit more into my research. And I want to try to answer with you this question. What are the ingredients of a good sea ice simulation? I'm Italian, so I will use a very Italian metaphor. which is pizza. So I see a lot of parallelism between pizza and sea ice. They're both very flat, heterogeneous. Thermodynamics is very important for the final result. But yeah, try to follow me here. We need a couple of things for making good pizza. On one side, we need a good recipe and good ingredients. And this is kind of the way we build our sea ice model, the way we parameterize the processes. But we also need a very good oven to cook the pizza. And these are the boundary conditions that we apply to our sea ice model. We can have the best ingredients, the best recipe, but then if we don't have a good oven to cook the pizza, the result will not be great. And the same is true for a sea ice model. If you force it with bad boundary conditions, then you won't get a good sea ice output from your model. So in my talk, I will try to focus on these two aspects in the context of the heat conduction during winter. And we will start with the latter, with the oven. Typically, the boundary conditions for sea ice models are reanalyses. At least at the development stage, we use atmospheric reanalyses to force these models. Atmospheric reanalyses, I think they are interested. They are very much used, I guess, also by you more atmospheric people. And in the Arctic, they have issues, which I will describe in the next slides. So what I'm presenting here has been recently published in Monthly Weather Review. So if you want to have more details, I encourage you to check out the paper. So this is the typical sea ice description that we have in a coupled model. It could be a CMAP model. As I said before, we discretize the sea ice in multiple thickness classes, which evolve in space and time. And on top of each thickness class, we have some snow, right? This makes sense. If we look at the assumptions that are made in atmospheric models that are used to produce reanalyses, for example, ERA5 or JRA-55, the situation is very different. First of all, we don't really have the concept of sea ice cover, sea ice concentration. We have just a binary ice cover, either 100% or 0. We have a constant sea ice thickness in space and time everywhere, and we don't have snow over sea ice. And yeah, just as a reference, this constant sea ice thickness is 2 meters for JRA-55, 1.5 meters for ERA5. This is a very crude assumption, and it brings some issues. In particular, there is a well-known warm bias over sea ice in winter, which was described in this very nice paper by Yuri Batrak and Malte Müller at Norway, which I encourage you to read if you use reanalysis in the Arctic. Let's try to understand what's the situation. So if you imagine that the reanalysis sea ice has a constant thickness of 2 meters, and your real world sea ice is thicker than that, what happens is that in reality, the conduction will be less from the ocean to the atmosphere. And so this equilibrium temperature that you will get at the top will be colder than what the reanalysis says. And in this case, we have a positive surface temperature bias. We also have the opposite case, where the reanalysis sea ice assumption in thickness is an overestimation. The real world sea ice is thinner, there is more conduction, and so the real temperature is warmer, and in this case, we have a negative surface temperature bias. How large are these biases? So here you can see a comparison between reanalysis and observations at the MOSAiC site. In particular, this is for ERA5. Let's focus now on the orange curve, the original reanalysis, and the MOSAiC observations. You can see that in some instances we have biases up to 10 degrees. Now, if you imagine you take these reanalysis and you use them to force your sea ice model, and you have 10 degrees warmer atmosphere, the results that you will get will be very different. And that's why we want to fix this reanalysis to provide, first of all, better reanalysis state, but also better boundary conditions for our models. And yeah, in the next slides, I will try to explain you how we try to go from the orange curve down to the black curve. So this overestimation, I forgot to say, is particularly strong in clear sky conditions. So when the surface can effectively cool down, radiate in winter a lot of energy back to space, and there is no solar radiation compensating. Yeah. So this is when the temperatures in the Arctic get colder. So the mechanism that we use is a very simple machine learning bias correction model. On one side, we have a lot of observations of the surface temperature from satellite infrared sensors that are currently not assimilated in reanalysis models. We have these observations, we have the reanalysis, and we can quantify the difference. And then, of course, we don't have observations everywhere all the time, also in the past. So we need to build some predictors, or to choose some predictors, which can be reanalysis fields themselves. So in this case, we use the surface temperature, the downward long-wave radiation, which is a good proxy of the cloud state, and then sea ice thickness and snow thickness reanalysis products from biomass and snow model, and the Lagrangian snow model. And then basically we build a fully connected neural network which connects these predictors with the bias. Once we have established this connection, basically the correction is just the opposite of the bias. That's the basic principle. We can do this only in clear sky conditions for one big reason. So when we have clouds in the Arctic, the satellite sensors cannot see the surface of the ice. They will just measure the temperature at the top of the cloud. So we can really quantify this bias well only when we have clear sky condition, but incidentally that's also when the biases are larger. So yeah, it works well for us. Just so you keep in mind, reanalysis can be very different in the Arctic. They are heavily under constraint, and this is when it comes to total cloud cover. You see the representation of ERA5 and JRA-55. It's completely different, and here you can see kind of the real cloud state as seen by MODIS. So you can see in the case of ERA5, the cloud cover is way overestimated. But then if you look at the long wave state, actually the cloud cover in ERA5, it's much more convincing than in JRA-55. So there are a lot of technicalities in this, in the way we apply this correction scheme, and they are a bit better described in the paper. I will not go into detail now, but just keep in mind that the cloud state is important. So here I'm showing the prediction. I'm showing the temperature bias as a function of the prediction of the predictors for our machine learning model. Here you can see the atmospheric predictors, and here you can see the sea ice predictors. And you see that this cloud of point kind of makes sense. So the bias is larger for thicker sea ice and thicker snow, and it tends to be negative for thin ice and thin snow, and this is consistent with the principle I described before. And at the bottom you can see the correction predicted from the machine learning model, and you see that it can capture quite well the features of the bias. So once we have this, we can apply the correction at the reanalysis field. Here you have the original ERA5 skin temperature. This is the corrected skin temperature. You can see that it's colder, in particular in clear sky regions. And this makes sense, and we do this at every time step of the reanalysis. So the correction is also consistent with the weather and kind of evolves with it. Of course, we need to compare this correction scheme with independent measurements to validate the quality of our model. And we do this comparing our corrected reanalysis to MOSAiC observations. And I think we need to be a bit careful when we do this comparison. I argue to compare well models and observations, we need to make sure that the clear that the cloud state is compatible, otherwise it's not an apple-to-apple comparison. So you can see that when the long wave radiation downward difference between the analysis and MOSAiC observation is small, we have a very good skill score, so it means that we are improving the reanalysis. We are also improving the reanalysis in other regimes, but in this case, I argue this improvement comes from the wrong reason. So we really should judge the skills only when we have comparable cloud states. And this is just show the improvement if you consider all the available observations. You see that in particular for ERA5 we get 27% improvement in terms of skin temperature and error reduction. And of course then based on how we design the metric we will get even larger improvements if we only focus on the clear sky cases. But overall it works better for ERA5 than JRA-55, and we are still investigating why this is. Once we have the correction, we can see how it looks in a more average sense. So here I have average for DJF, March, April, May, and fall months, and you can see that you can see the imprint of the sea ice thickness on the correction. You can see that there is a certain seasonality. It's stronger in winter and spring, and it's less strong in the fall. And this is because in the fall the sea ice is thinner, and there is also less snow basically on it. If we look at, now let's focus on the uppermost plot. This is a kind of a similar overview. We have the year seasonality, and in this case I split the difference between corrected and original reanalysis field in different decades. And what you can see is that the strength of the correction that we apply kind of decreases with time. So, and this makes sense to me because it means that because of course the sea ice changed quite a bit in terms of its thickness, and the current sea ice state is more compatible with the reanalysis assumption than the past sea ice state that we observed at the end of the previous century. We also then did the final check. We computed the kind of temperature anomaly in the Arctic. Of course, you can see there is definitely warming. We computed it for the original and the corrected case against their own climatology, basically. And you can see that there are small differences. In particular, the corrected reanalysis seems to warm a bit more than the original case, but these differences are tiny, I would argue, and inside the observational uncertainty and the uncertainty between different reanalysis products. So this means basically that we didn't break completely reanalysis by applying with the correction, and that it stays consistent. So as a summary of this first part, the correction is state dependent. It's consistent with the observed sea ice conditions and with the weather. It targets clear sky events, and this makes sense because we know that the bias is more pronounced during clear sky events. We can also correct for cold biases that occur on thin ice, and this was not the case for previous correction methods that have been attempted. And the self-emerging property of the correction is an interannual trend consistent with the declining sea ice. And provocative question might be, why do we still force our simulation with reanalysis? Why don't we do model development directly in a coupled context? And I'm happy to discuss more about it later in the discussion. Just to conclude this first part, I want to mention that this is just one avenue. The other approach that operational center are using is to correct their models, so to represent well the sea ice and the snow on top of the sea ice. And this has been done at UW, for example, and it will be available in a few years when ERA6 will be released. But in the meantime, we have a solution at least for the current generation of the analysis. Now, let's move to the second part of my talk. Let's see how am I doing with time. Perfect. So, some considerations on the formulation of sea ice models and the winter heat conduction problem. So I like to have this sketch in my presentations to kind of show a bit like how the development, how I see the development process for the sea ice model. Just imagine this sea ice model is a very big piece of pizza dough that everyone wants to stretch. We have different interests. We have some people want simple implementation, right? Some other want complex physics and a more process-oriented model. People want high resolution because high resolution is important, particularly for the ocean. And we want computational efficiency because we want to run large ensembles. And yeah, in the end, there is a lot of compromising to be done. And not to mention that the same model needs to be used for climate simulations, but also for operational predictions, so very different test cases. So yeah, what I will mention in the next slides, try to think about it in the context of all these competing interests. So where do we stand? I already described before this scheme that I prepared, representing all the subgrid parameterizations currently active in the model that we are using at NCAR, so CSM. And what's missing? Where are we going next? So processes that are not represented currently in model are snow metamorphism and redistribution. So once the snow falls over the sea ice, it stays there, it doesn't move. In reality, that's not the case. The wind moves the snow around, the snow is compacted. If it rains on the snow, then I mean, you can see the snow outside and see how it looks like. It's not very different in the Arctic. Another process that we don't have heterogeneous sea ice and snow density. The density is a constant everywhere, and the same is valid for the conductivity. And we know that, of course, this is not the case. There are big differences, and so we are trying to improve on these points. So what's holding us back? There are discrepancies between the observed parameters and the model parameters, so you cannot just take a measurement that's done of the snow conductivity, for example, done in a lab, plug it in your model and expect that it works, because there are a lot of approximations in these equations. And yeah, so it's not as simple. Sometimes it works, but most of the time the sea ice state that you get is not satisfactory. Then yeah, there is this lack of prognostic sea ice and snow density description. So basically, we don't really take into account the density evolution of these mediums, because that would make the advection problem much more complicated. So yeah, that's a compromise we need to do when it comes to sea ice. There is also a certain unwillingness of introducing more and more variables that we cannot compare with observations. So what's the point if you cannot verify your prediction? And also there is a certain uncertainty about the effect of these new parameterizations. So you do a lot of work, you implement a very complex scheme, and then it doesn't have climate relevance. And yeah, of course, this is something to think about. And in the next slide, I will describe our strategy to overcome these issues, basically. Fortunately, with MOSAiC, so it was an expedition that happened in the Arctic between 2019 and 2020, we had a lot of new observations, in particular very, very nice winter observations of the Arctic sea ice. And what I will focus on today are these freeboard and surface temperature measurements. These are very, very high resolution observations. So the freeboard resolution is 0.5 meter and the temperature resolution is 1 meter. This means that we kind of have a natural solution of the sea ice thermodynamics from the observations, and we can relate what's the impact of the heterogeneity, so the topography of the ice on the temperature, and how this controls the heat that flows through the ice. You should keep in mind that it's winter. Just imagine it's -30 in the atmosphere. The ocean is at freezing temperatures, so 30 degrees warmer, and there is kind of this sea ice, which is sort of as a blanket covering the ocean and inhibiting the heat exchange. And this is the snow freeboard, so it's defined as the distance between the surface of the ocean and the top of the ice or snow, like the interface with the atmosphere. Okay, when you try to make a scatter plot of these two fields as they are provided by the MOSAiC providers, you see some weird things going on. In particular, you see that there is ice with higher freeboard, so thicker ice, which is warmer than thinner ice. This doesn't make a lot of sense. And yeah, the problem is that if you put the two fields on top of each other, there is mismatch. So there is mismatch that depends on the helicopter flight. It's flight dependent. And we developed a correction scheme to fix this, which works well. So I won't go into the details now, but we kind of can collocate this measurement so that we have the temperature signal of the ridges, on the ridges, and on the level ice, on the level ice. So, yeah. This took quite a bit of time, but we're happy with the result. And yeah, now if you see how it looks like, it makes much more sense. So the thinner ice is warmer because it insulates less the atmosphere from the ocean, and the thicker ice is colder. You can also refine this method even further by correcting the freeboard based on the temperature, but I won't actually use these orange points in my presentation. Let's stick with the blue ones. So now we can take these observations and kind of look at them through the model lens. So what we typically do in the model is to discretize the ice in multiple thickness classes. We can also define the freeboard classes. In this case, we have freeboard observations. And the way of reading this plot is that, here you have gray horizontal lines, and these are boundaries between thickness classes. And so this is the sea ice concentration. So a bit more than 20% of the ice falls in the first freeboard category, so as an ice thickness between 0, or as an ice freeboard between 0 and 15 centimeters, and the mean of the ice that falls in this category is this, like 12 centimeters. And yeah, you can do the same for the other bars, and the color of each one of them represents the average temperature. So you can see I don't know if you can notice, the first class is a bit warmer than the others, but given the color bar that I chose, like, everything looks very flat. This was very surprising to us because we were expecting to see big surface temperature differences that we didn't find in observations. So we have a freeboard, we have models, and we can ask, okay, given the observed freeboard, which equilibrium temperature would the thermodynamic model predict? And in this case, you can see that there is much more heterogeneity. So this was the situation from the observation, and this is how the model looks like. You can see that we still have this warm temperature kind of in the open leads that crosses the domain. But then over the rest of the ice, the ridges So the thick part is kind of correct, but then the level ice is much warmer. This means that the model has too much conduction compared to the observations, or at least that's a strong indication that that's what's happening. So we have multiple flights, and again we can see like the observation on top and the model prediction for the same flight at the bottom. And you can see this is quite a consistent feature that the thinner sea ice classes are too warm. This is kind of the model minus observation. And of course we have various hypotheses for this. So it might be that the sea ice conductivity is lower, like that the sea ice system conductivity is lower for thinner freeboard classes. This is a possibility, so maybe we need to come up with a better parameterization for the conductivity. It might be that more snow accumulates over thinner sea ice. I don't think this is the case, but it's an hypothesis that we cannot exclude at the moment. And since the snow has is a much stronger thermal insulator, it would kind of keep the thinner ice colder. And it might also be that that this observational model is not really compatible. So just imagine that what you're measuring with the thermal camera from the helicopter is basically the temperature of the snowflakes at the top. On the other side, you have a model which is discretized in big chunks of vertical layers. So the responsiveness of this can be different compared to the real world. Okay, so when it comes to parameterization for the conductivity, we could basically build a functional relation between the temperature error and the conductivity correction that we should apply to the system to get this temperature error fixed. If we link the sea ice state, so the state of the freeboard distribution or the ice thickness distribution, to the temperature error, we kind of can build a parameterization. The link can be a functional relation, can be a neural network. It really depends on the complexity of the system. I won't go more into detail now about this because I think we still have a question mark, and we are not 100% sure that the conductivity is the whole story. So first of all, let's discuss a bit some caveats of this approach. So since I'm working a lot with freeboard, I don't really have, I cannot quantify the separate impact of sea ice and snow. Kind of we can look at them just as a combined system, but it would be nice to explore. I think the snow is to blame more than the ice, for example. Then we don't know if the snow conductivity representation is the whole story. It might be that we are playing with the conductivity, but in reality the bias can also come from the bulk formula that are used in the atmosphere to compute the heat fluxes and the vertical discretization, as I said before. Also in the model at the moment we cannot have sea ice with no snow on top, and this is also a limitation that we are trying to address. And also the thermodynamic model that I'm currently using is a simple one, so it's kind of more on the zero-layer model side that I showed you before, rather than the complex one that's now in CSM. So there is a question mark on how applicable are these results to a more complex model. Okay, and this brings me to my next couple of slides, which are the last one. And yes, let's try to use a more complex model formulation. So we typically just have the freeboard, but actually in the MOSAiC site, we also have some transit. So people walking on the ice and measuring at 1 meter resolution the snow thickness and the ice thickness below. And here you can see one of these transects where we have basically some level ice. Here, basically in blue, you have the ice thickness, which is negative in my case. In orange, you have the snow thickness multiplied by 10 just to enhance a bit and make it more visible. You see that there is a flat part, and then there are a couple of ridges. Maybe here and here you might be able to see refrozen bits. So there the ice broke and then it refroze. And what we can do is basically to have, in this case, full thermodynamical model, so solve the heat equation with the finite element model, discretizing in a very fine way this domain, and then looking at how the temperature varies in the ice. And I think we can learn together something about the sea ice thermodynamics and what the situation is. So let me slowly guide you through these plots. They are a bit busy. So in the first one, we have a 2D solution. So we are allowing the heat to flow vertically, as we typically do in sea ice models, but also horizontally. I mean, it's all connected in reality. It's not that we have separate thickness classes. And this is the temperature for the same length of the transect at the bottom, so at the interface between the ice and the ocean, and there the temperature is always freezing temperature, right? Because it's a melting condition. This is at the middle of the ice thickness. In red, you have the interface between the snow and the ice, middle of the snow, and this is the top. In black, we have the observations from the helicopter, thermal infrared that I showed you before. And in green, we have the zero-layer model, so the simple one that I was using. You can see, first of all, that the zero-layer model actually does quite a good job. It's almost spot on top of the full-blown thermodynamical model. Then, what can we learn? So you see again, if you compare the observations to the model, you see again this bias that we have for level ice, whereas the ridge is actually quite nicely captured. And then, I didn't mention it, but on the right-hand side, we have the 1D solution. So we just allow the heat to flow vertically and not laterally. And you can see that basically what this is kind of the difference between the 2D minus 1D. So what we can see, first of all, is that the surface temperature and the interface temperature are anti-correlated. And this is a bit counterintuitive, but it kind of makes sense if you think that when more heat can escape at the surface, we can cool more effectively the ice below. Whereas when we isolate more the surface, the ocean can warm the bottom more. So I think this is very cool. And the first time I saw these plots, I didn't think about it. Another thing that we notice is that while the variability at the surface is very, very small, so this curve is flat, the interface temperature is all over the place. It really depends on the heterogeneity of the ice, but mostly of the snow on top. Of course, in the 2D case, this curve is a bit smoother than the 1D case because, like lateral heat conduction, it kind of smooths the temperature here, right? This is also, this makes sense. You also see that if you look at the temperature difference, the 2D case, it's slightly warmer than the 1D case, and this means that we can extract more heat through the ice because it can also flow laterally and reach hotspots where it radiates to space. Now, I also tried to play with the conductivity of the snow. So again, 2D solutions. The only thing that changes is the conductivity of the snow layer on top. In the left-hand side, no, in the right-hand side here, we make the snow less conductive, so a better insulator. And you can see that this brings kind of the surface temperature down, which is what we want, right? Reduce kind of this bias. On the other side, you see that making the snow less insulating has a huge, huge impact on the sea ice temperature. So we want to be sure that we are doing the right thing here. We cannot just change one parameter, try to fit better some observation, but then ignoring the fact that we are moving this interface temperature up 10 degrees. And of course, the temperature that the ice has at the end of the melting season will be very impactful than in summer when the ice basically warms up and starts melting. So yeah, the message that I want to convey is that we really need to focus, to be strict with our diagnostic, to focus on the processes, and I think it's not enough anymore to have a model that simulates well the sea ice extent or the sea ice thickness in a panarctic sense, but then it does that for the wrong reason. So what we are trying to achieve with the next generation of models, kind of CMIP 7, is to get all these small processes and balances right, because only doing this we can really we can be confident about the prediction that we do in a climate change kind of setup when we run the model into the future. So I promised something about machine learning in the context of sea ice modeling. And I want just briefly to mention that for sea ice, the situation is a bit different compared to the atmospheric and ocean model. So what's done in ocean and atmospheric model is to run high-resolution versions of the model and then learn how to parameterize the low-resolution version based on the high-resolution simulation. This works for these two mediums because kind of the eddies emerge from the basic equations, basically from the Navier-Stokes equation. It's not the case of sea ice that really relies heavily on empirical parameterization. So I can run my model at very high resolution, but if I don't have the processes right, this will not magically emerge. And yeah, that's a difference to keep in mind. But that said, machine learning can be used to enhance observations, can be used to correct the model output. We can also think of building kind of neural networks into the model. We just need to make sure that there is an harmonization of this parameterization with the rest of the model infrastructure. And also, since this development process relies a lot on observations, there is always a disparity between Arctic versus Southern Ocean. So we might end up fitting a lot towards the Arctic, but then, I mean, the same model and the same physics, keep in mind, should always work also in Southern Ocean. Okay, so with this, I finish my presentation. Thank you for your attention, and yeah, I'm happy to take questions.
All right, questions for Lorenzo?
I was wondering why you're using a specific machine learning model using projections, or if there's you try multiple things and that's the one that works best, or if there's another one that you're hoping to try out later.
Yeah, that's a very good question, and I will give an honest answer. So it was my first kind of machine learning problem that I tried to solve. So I started from the simplest kind of neural network that you could implement, and it turned out to be good enough. I mean, it worked well. We captured what we wanted to capture. So we didn't really try to go more complex than that. For example, having CNNs and taking into account convolution over stencil. We just wanted to stay local. Like, now thinking back, probably a nonlinear model like could have a nonlinear regression could have also worked. I mean, again, it's a neural network, so it's something very similar. But there was nothing really. There is nothing really special about it. It works as it happens with machine learning models. Like I think yeah, often there is not a lot of thinking about the model at a certain point when it works. Yeah. Yeah.
Yeah. So you've used machine learning to correct your sea ice temperature. Can you apply the result to correct the sea ice thickness as well? Because you found a correlation between having a cold bias and cold bias is how much thickness you have.
I mean, we need to, I think, no. I think the short answer is no. I will try to explain why. So we need to trust something. Either we trust the surface temperature in the analysis, and then we assume that the thickness is wrong, or we trust the thickness and then we assume that the surface temperature is wrong. I think probably in reality they are both a bit wrong, and you could in principle formulate a thickness retrieval based on the temperature error. We didn't do that. I believe, yeah, it would be not as accurate because the insulating property of the system doesn't depend only on the sea ice thickness, but also on the snow that we have on top, right? And they have two different conductive properties, so it's very hard to invert the problem in a meaningful way. I don't know if it makes sense.
Excuse me. I know we talked about this morning, but it's fascinating how the spatial scale that you're looking at is so kind of tight here. That's very interesting to me. If you look at which I'm sure you have, a drifting buoy, and we talked about the issues with locating where the thermistor temperatures actually are in the profile, but the skin temperature with the time buoy data that I've seen varies much more than the interface temperature. So in time, that the black, if 1 point drifting, the black line varies much more than the red line, whereas in space, the red line is varying much more than the black line. I find that just kind of really interesting, and again, attests to how insulative the snow is, because signals in the temperature of the surface of the snow aren't very quickly at all translated to the ice.
Yeah.
So yeah, I mean, that's interesting to me. And second kind of related point is that snow ice interface retrieval I was telling you about. Whether it's right or wrong, I don't know, but the depth of the snow has a major impact on what the interface temperature is.
Yeah, and you can basically see that here as well. Here we have a point with a lot of snow. There is not a lot of difference at the surface, but then when we basically we run this thermodynamic model to equilibrium, there is not really time derivative in this. But yeah, you can see the big cut that it has, like really insulates a lot. This ice below, and then the ocean can warm it up from the bottom. But it's interesting, this like spatial and time scale separation. That one, if you remember, I don't know, the comparison of the skin temperature at MOSAiC side, where we have these huge fluctuations. Yeah, maybe I can. Sorry for scrolling back very quickly. But yeah, you can see how the skin temperature varies a lot in what you were saying, and at the same time, it spatially also the interface temperature varies so much. Yeah,
that's interesting.
Yeah. Rupert?
Yeah, very great talk, Lorenzo. My question is about the reanalysis data set bias correction you did. I'm wondering if you checked what happened to the total energy balance at the end. Like once you introduce the correction, whether the outgoing long wave radiation and the incoming short wave radiation budget matched up with the satellite observations, because I know that there's a lot of issues in reanalysis data set with that balance. Have you looked into that yet?
No,
Okay.
because what we do with this correction is just cherry pick one field, right? And we fix this. what we can do is to recompute, kind of based on the new skin temperature, we can recompute the energy emitted by the ice, but then to get the since it's not coupled anymore, right? We cannot get it to be consistent with the rest of the radiation stream in the atmosphere. So, yeah, I mean, there is no real way of kind of based on this correction, propagate this information to the rest of the reanalyses higher up in the atmosphere. Yeah, that's of course the limitation of our method. On the other side, the main purpose of this is to then take this surface field and use them as boundary condition for the sea ice in the ocean. So kind of what comes from top down and the surface layers are enough. But I would argue the best approach is to fix the physical representation in the reanalysis model. And in this case, then if you then represent correctly the snow, you get all the coupled processes also right and consistent. Keep in mind that anyway, reanalysis are, or weather forecast models are not energy and mass conserving, so yeah, they're not perfect.
For your machine learning model, are you initializing the weights randomly, or is it assigning them itself, or are you assigning them to start with?
I think they're initialized randomly, and then they adjust basically very quickly to the.
So the follow-up question is, do you run it kind of multiple times to see what the variation then is in the weights that are as it's training, or is there not much fluctuation there?
Yeah, I think of course, since the training is random and it's done on batches, every time we do the training, we get slightly different outputs, right? We check the weights and they don't really change so much. So they are pretty stable. I'm not arguing that we can interpret these weights and kind of explain what's going on in this neural network, but at least it's the structure remains pretty consistent.
So like the fluctuation is within a reasonable amount, and it's not like the
Yeah. So to be honest, it's not a very difficult problem to learn for the machine learning problem. So you can see like this structure. It's not crazy, right?
Thanks.
Any other questions? Yep.
Hi, thank you for the talk, and I think this might be a very naive question. I'm not a CIs person, but if I'm understanding correctly, basically, first part you're showing that how CI's thickness bias could be relating to biases in temperature, right? You're correcting for that. And then part two, you're looking at how in like the specific observation you see that freeboard height differences do not matter for temperature changes. So that means that the bias in part one of the study may or may not be coming from thickness changes. Is that right? If so, would you like do the part one study differently, or like set up the input parameters in your machine learning model? Would you set them up differently?
Yeah, I mean it's a very interesting question. So, I mean, you're correct. In the first case, I argue that this kind of thickness bias that leads to a temperature bias. And then I show that the freeboard doesn't really matter. I think the key here is to understand that the freeboard doesn't matter after a certain point. So when the ice is very, very thick, it's already a good insulator. And then when you add more snow on top, then of course the surface temperature will not respond as much. But of course for thinner ice cover, then yeah, it matters. And also you should always keep in mind that it's not only about the ice thickness, it's particularly about the snow. So the ice thickness has a conductivity of 2, whereas the snow conductivity is between 0.1 and 0.3. So the snow, since it's full of air bubbles, is a much, much better insulator, and a little bit of snow can make a big difference if you have if the ice is not already too thick. But I will think about it because now it's a good point that you raised. And also keep in mind that on one side, the reanalysis has a resolution of 35 kilometers. So it's an average of a lot of these flows and open leads and ridges. On the other side, I'm looking at the meter scale or sub-meter scale. So yeah, they kind of are different problems to fit. Yeah.
Okay. Other questions? Okay, if not, let's thank Lorenzo.
I just wanted to say that I'm here also tomorrow if you want to keep discussing more. So just drop me an email or drop Rudra an email, and